Okay, first of all, welcome to this new academic year and fresh semester. And for all the PG students, warm welcome to IIT Kanpur. And by extension, warm welcome to this course. So if you don't know already, this course is E610 Analog IC Design 1. So if you are here for some other course by mistake, last chance to leave, because I locked the room in 5 minutes and you can't leave. So everyone is here for this course? Okay, good to know. Nice. So yeah, before we get into the technical content, as is the convention, I'll give a brief introduction and motivation. And that goes as follows. I'm sure in the last couple of years, the word semiconductor chip design are some of the most commonly seen terms in newspaper articles, media outlets, and so on. Right? So much so that common man has some understanding of what these terms mean. But this was not the case 10-20 years back, right? Because let's say 10-20 years back, if someone came up to you and asked what you do for a living, and you told I'm a chip designer and I design chips for my living, very high chance that they would have thought you are working for a company like this, designing chips like these. But of course, that's no longer the case. Now people do know what you are talking about. They know these are not eating chips, although they're nice to look at. These are semiconductor chips. And semiconductor chips form the backbone of all electronic systems, valuable for the country's economy and so on. So which means if semiconductor chips are valuable for the country's economy, chip designers, which are you guys, you are even more valuable. That's about it. Okay? And it turns out if you take chip design, you can have two broad classifications. One I will call it to be a fully analog design, and the other is a fully digital design. Now that begs a question, right? If the entire world is going towards digital, right? You want digital payments, digital currency, digital India, everything digital. What's the reason to learn analog? It's a valuable question, a valid question. And the obvious reply to that question is this following. Of course, bulk of the information is now stored in digital and processing is more efficiently done in digital domain. But this information has to come from somewhere, and that is from the real world. And unfortunately or fortunately, the real world is still analog. So which means we need to have both. That's all. And yeah, for example, let's say you might have downloaded your favorite, T16. What is the course? What is the course name? Okay. Yeah, so you're saying, you might have downloaded your favorite, A. Rahman or Ed Sheeran song on your phone, and they'll all be stored as ones and zeros. But remember, when the song was initially recorded, singers were singing, people are playing instruments, they were all analog signals. They had to be processed in the analog domain. Some analog signal conditioning circuits were needed, and then you need to have an analog to digital converter. All of these analog circuitry have to be there before it gets converted to ones and zeros. And similarly, if you play the song back, the digital signals on your phone need to be converted to analog signals first. A lot of analog processing has to be done, and then it has to be finally played onto your speaker. This is again an analog circuit. And of course, if you can't only have analog and digital, you need to have a translator in between, and that's where we have analog to digital and digital to analog converters. So if I call this analog digital, this typically we call as mixed signal circuits. And even if you take a proper digital block like a microprocessor also requires a whole bunch of analog circuits for it to function well. Right? For example, a microprocessor is rated to work at a particular supply voltage. It has to be held properly constant. And who does the job? We have voltage references, voltage regulators, truly analog circuits doing the job there. And microprocessors, runs at some particular clock frequency. You can't imagine that I'll extract clock from thin air randomly. You need to have dedicated circuitry doing that. So once again, you have a whole bunch of analog circuit. So bottom line of the discussion is the following. If you want to build a powerful electronic modern system, you can't only do it only in the analog domain or only in the digital domain. You need to have an interplay of all. You need to have analog, mixed signal, and digital system. And in this course particularly, we'll be focusing on analog. If you already didn't know, that's what this course is about. And that said, I'm sort of assuming that everyone here has taken some analog circuits course before. I'm hoping PGs have done some analog circuits course in your undergrad time. and UGs, if you are here, you might have taken hopefully E210, right? Of course, I'll start from scratch in this course. So in the first couple of weeks, I'll cover the relevant basics so that everyone is on the same page. But yeah, but if you remember your old analog circuits course, the first couple of weeks should be like a recap of what you already know, maybe different perspective of yeah. So anyways, so it will should look like a recap of things you already know, maybe filling some gaps in your understanding here and there. That's how it should look like. So this should be like watching the highlights of a cricket match that you have already seen. Should clearly know what's going to happen at each ball, who's going to get out. At the end of the highlights, you should not be surprised to see if India lost the match and Australia won the match. Right? That's the idea. The whole essence, hopefully it should be like bringing some bell here and there. That's how the first couple of weeks will go. Okay, that said, I've shared the first course handout. Please go through that for all the course related details. So the grading policy is this: we'll have mini quizzes and design projects accounting for 45%. Mini quizzes, I'll have 5 of them, and if I take 5 mini quizzes, I'll take best n-1 out of n, which is basically if I take 5 quizzes, I'll take best 4 out of 5. And the tentative dates for those mini quizzes I'll send out shortly. You can mark your calendars. And if you are not added to the course MOOCkit page, send me a mail so that I'll add you immediately, because all the course announcement, all the materials will be posted in this MOOCkit page. And other thing I want to, before I forget, so typically I take some extra classes in the beginning of the semester, and if I do it, I'll not take classes in the last week of the semester, because last week everyone is occupied with all other things. So technically they're not extra classes. I'll borrow the classes in advance and take it. Right? So again, tentative schedule for those advanced classes also, I'll send out a mail by this weekend. So again, mark your calendar. So I think that's about that's all the logistical information I wanted to convey. So since that is sorted, let's actually get started with the course. And again, remember that this is a long lecture hour, 75 minutes course. So if you have any doubts, feel free to pause and ask me questions, because if you miss something, you might not follow what follows after that. So then it will be like watching some Korean TV series without any subtitles. Okay. So make sure you are on the same page with me. If you have doubts, feel free to stop. Okay. So the focus of this course will essentially be making or designing this triangular block. Much easier to draw than to design, or maybe at the end of the course it becomes as easy to design as well. And what is this block? Yeah, sure, everyone knows it's op-amp. So if I call it, let's say if I mark these voltages as V1, V2, and if I say this is A, what is the output voltage? V1 minus V2, that's it, into A. And an op-amp is what kind of controlled source? Voltage controlled? Remember the output is a voltage. So at the output it is a voltage source or current source? Voltage source. And the voltage depends on what quantity? Current or voltage? Difference between two voltages, right? So what kind of control source is it? Voltage control, voltage source, VCVS. Okay. And ideally, what do you want the gain of this op-amp to be? Ideally, if I give number, what will the number be? Infinity. Okay, so that begs a question: why on earth will I make some block which has an infinite gain? Because if it has an infinite gain, I give any signal, output is infinity, or in practice it will saturate to the op-amp supply rates, right? So why do I want infinite gain block? Yeah, remember that. I'm sure everyone has seen this. So we have seen this classic negative feedback model. So what is the closed loop gain here? Everyone has taken a control systems course. So this is something you might remember. What is this? Closed loop gain from, let us say, if I call it x to y. How much is this? A by? Fine. And if A is really, really large, what does it approach to? 1 by? If A is very large, this is what is going to dominate. Here you have A, it's 1 by B. So remember, this is the nice thing about negative feedback, that it doesn't matter what my A is. A can be 1 million, 10 million, 100 million, doesn't matter. Even if this A value changes a lot, the final closed loop gain is fairly constant, right? So this is how you get accurate and precisely controlled gain, and this is what you want in practice. I want something which is well known to me, well controlled and accurate. So that is why we want to have negative feedback systems, and this is exactly where the op-amp is comes. Because for this negative feedback system to work well, you want the gain A to be as high as possible, and that's where you want to make op-amp. And of course, negative feedback systems are not something that we teach so that we can ask you extra questions in exams, and that has so many real life implications. In fact, I would say if you are alive at this moment, it is because of negative feedback. Because all in your body, the way temperature is regulated, the way your blood glucose level is regulated, everything is based on negative feedback. And a common example I give for negative feedback to appreciate is this, right? See, anytime you speak normally, that has an inherent negative feedback action in it. Allow me to explain. So let us say you want to talk, and let us say you want to talk to some person in front of you. Your brain kind of knows what is the optimal loudness level with which you have to speak, so that the person in front of you can hear properly. Right? So let's say the brain already knows what is the optimal level with which you have to speak. So if you think about how this is accomplished, you basically speak. I model you as a speaker. Whatever you are speaking is heard back by your ears, and then your brain kind of compares it with whatever you are hearing back, and then decides whether you should speak more louder or less loud. That's how you are able to speak at an optimal loudness level. You are not randomly increasing your loudness or reducing your loudness. And an extension of this example is even more relatable. So I'm sure most of you might have recognized this, right? If you are wearing some over-the-ears headphones covering your ears, you tend to speak much louder than you anticipated it to, right? Why does it happen? Well, use the same model. The moment you have earphones, what you are speaking is not completely fed back. Only a small fraction of it is fed back. So the closed loop gain, it's 1 by beta. Of course, this will be greater than 1 because beta is smaller than 1. Okay? So negative feedback system is basically how the entire world is functioning, entire world is stable. And to make negative feedback systems, we need to have a good op-amp. So that's the bottom line. You don't make op-amp so that you use it in open loop. An op-amp is always meant to be used in closed loop. Right? That's the first thing they should always have in mind. Okay, cool. So now this is known. Now tell me, an op-amp, when I say it's an op-amp, it is an amplifier. When I say it is an amplifier, what is it trying to amplify? Yeah, signal, but signal can be anything, right? Let's say we put 1 roti here, you will get 10 rotis at the output. It's trying to amplify voltage. Yeah. That's okay. Difference of what? Voltage. Okay, see, if I just want to amplify the voltage or magnify the voltage, the simplest thing you can do is to use a step-up transformer. You might have learned it in your... So, we'll come to that, correct. So, this is the simplest way to amplify voltage. But this is not what we call as amplifier, right? So, when we say it's an amplifier, we are not talking about voltage amplification. We are actually talking about power amplification. Because in transformer, the voltage might increase, but the power, what happens to it? It's constant, right? So when we talk about amplifier, that is the other thing you should always remember. So these are the minor gaps I would want to fill in. So when I say I'm talking about an amplifier, I'm essentially talking about getting some kind of power amplification. Okay. Cool. So now let's see how we can start making this from scratch. So let's say I have some signal source that I want to amplify. Again, I am drawing it as a sinusoidal signal, but in practice the signals you might want to amplify, they are not sinusoidal, they are some other signal. But centuries ago Fourier told that any signal I have can be decomposed as a bunch of sinusoids. So that's why we sort of deal and stick to sinusoids. So let us say this is some signal V in. Typically sources have an inherent source resistance Rs. Now my goal is to see what can I do to amplify the power. So let us say I have some device here. Let's say I have some network here. I'll call this N. And loosely speaking, I say this network has an equivalent resistance of R times N. Sorry, Rn. Okay. Now, then what is the output voltage here? If I call this as V out, what is the output voltage? V in into Rn by, yeah. Now remember that here the input current is same as the output current. So which means if I want to amplify the power, it is sufficient for me to amplify the voltage. So that's why we'll only look at the voltage gain here, but actually we are getting power amplification. That's our goal. Okay. So which means the gain I have here is this factor. So I have, if I take the magnitude of the gain, it is essentially Rn by Rs plus Rn. And how do you want this quantity to be? Greater than 1 or less than 1? Less than 1 or greater than 1? You want to amplify, right? That's your whole job. Okay? Greater than 1. Now remember, Rs is not something under your control. Rn is the only variable of choice to you. So forget about all the practicalities. Let's say this is a mathematical function I give to you. What would be the condition to satisfy so that this equality is met? Rn should be, if Rn is very large, what will be the, this approaches 1, right? I want this to be greater than 1. If it's a math function, see, I have numerator, denominator. If it's to be greater than 1, denominator should be higher or numerator should be higher? Numerator should be higher or denominator must be smaller. So if this has to be smaller than Rn, how do you think Rn should be? Should be negative. Right? For example, let us say Rs is maybe 100 ohms, and I choose Rn to be minus 99 ohms. I get a gain of how much? 99. So looks like if I have a negative resistance, my problem is solved. So why don't you go to market and buy a negative resistance and make an amplifier? Huh? Why not? I mean, there is one thing that, let's say, it is not available in the market. My question is there something fundamental that prevents you from inventing, discovering or finding a device like this? There's nothing limiting you? Doesn't matter. Voltage is negative. Voltage is a physical quantity. Voltages can be negative, right? Okay, remember that in practice, all the devices we have are passive devices. What do I mean by passive device? They can't? Yeah, they cannot generate power. They can dissipate power or not dissipate power. One thing they cannot do is generate power. And this is, let us say, the passive sign convention. Right? So let us say if this I call as voltage V and this is the current I, what is the power dissipated? V times I? I know for passive devices, power dissipation is how much? Huh? I mean, power is dissipated. So if I were to write power dissipated as a quantity, what is a mathematical relation I can have? What is an inequality I can write? No, that's not the thing, right? See, V times I is the power. That is the power dissipated. This power dissipated is positive or negative? Or strictly I should say it is non-negative, right? So it's essentially greater than or equal to 0, which means they can dissipate power or not dissipate power, that's all. So now let us say it sketch the IV characteristics of a normal resistor that you know. This is V and I. Let us say resistor is some resistance value is 10k plus 10 kilo ohms. How will the IV characteristic look like? Linear, but in which quadrants it will lie? Something like this. If I want to have negative resistance, how should the characteristic look like? Like this, negative slope. So based on this, can you tell me, can I have something like this? I mean, the idea is, if I want to have this Rn to be less than 0, the characteristic should lie in second and fourth quadrant. I know that in practice all devices are passive, which means V times I is always greater than 0. So in which quadrants the IV characteristic of devices should lie?
So it should second and fourth.
I mean, is it clear? Maybe I'm convolving it so much, right? See, I'm saying in practice all devices are passive, which means V times I is always greater than 0. If that is the case, the IV characteristics should lie in which quadrants? First and third quadrant. So, sorry? First and third. So, which means can I make something which has a characteristic lying in second and fourth? That's fundamentally preventing me from making it. Make sense? That's why you cannot get to go to market and ask minus 10 kilo ohm resistor. Because it is fundamentally not possible to make. Right? If so, you have free energy, but that doesn't exist. But of course, as I always say, we are engineers, should never lose hope. So, let's see what we can do. Let me erase this. See, I know that I need to have some kind of negative resistance. And I know IV characteristics can lie in which quadrants? First and third. Right? So, let me just write it here. My characteristic should lie in the first quadrant, let's say. And I should have a negative resistance, which means the slope of the IV characteristic should be positive or negative. I should have a negative resistance. The IV characteristic slope should be negative. So I can have something like this. Fine, this is fine. But of course, this characteristic cannot continue like this because then it will enter second quadrant. So what should happen to the characteristic now? It cannot enter the second quadrant. What is the other way for it to go? It should basically reduce, and at what point it should exactly pass through? Remember, I can only have in first and third. So which means from here it has to come here. So which means it has to pass through what point exactly? This is something I cannot escape. Right? So which means the characteristic might basically do something like this. I don't care, something happens in third quadrant. Let's not worry about it. Similarly here, it cannot go like this forever because it will enter fourth quadrant. What should happen? We cannot have it in fourth quadrant. So for a practical device, how should this characteristic behave? It should basically maybe do something like this or stay in the first quadrant. That's the only thing possible. Make sense? Exactly. Otherwise, it will go in the fourth quadrant. Yeah, that's also fine. Yeah. This way, anything. Something to do so that it lies only in the first quadrant. That's all.
So means it can go exponentially downwards also.
Yeah. But it should not enter fourth quadrant, right?
Yes.
I'm just giving some rough sketch. The idea is this is what you want, but if this is what you want, and the IV characteristic should be passive, this is something which should happen, and here it can do here something. So let's say, for example, I tell you that this is, let us say, 0.5 volts and 1 volts. Maybe not drawn to scale, but assume that this is 0.5 and 1 volt. So between 0.5 volts and 1 volt, this has a negative resistance. Now let us say I directly go and connect my signal source, and let us say the signal I want to amplify has a very small amplitude of say 0.1 millivolts. Let me erase all this. If I directly connect the signal here like this, do you think I will get the required amplification or no? Sorry? Why not?
So it is in millivolts.
Correct. So?
And
complete.
RS is negative.
RS is positive.
RN is negative.
I mean, remember that, see, this is my this is my device, correct? And I know that to get amplification, the slope of the characteristic should be how much? Negative, right? So if I directly connect this here, do you think the slope of the characteristic will be negative? Yes or no? Because I am giving 0.1 millivolt, so maybe it will be somewhere here. Here the slope is not negative, but I should make sure that I am somewhere here.
Yes.
So in addition to this, what should I add? What's that? Some DC battery source, right? So let's say I add a DC battery here. So let me call it VB. Now remember, the whole purpose of this DC source is to make sure that this device here is operated in the required operating region, because this is the region in which you want to work. So which means you have to have this, no escape. Makes sense? And of course, as you some guys already mentioned the name, this technical jargon for this is DC biasing. And let us say nominally, or let's say optimally, I would want to be somewhere here at middle, let us say 0.75 volts. And this point we'll call as the DC operating point. I'm hoping biasing operating points are terms that you have already heard. Okay. If not, it's okay, you can learn it now, not a big deal. So this is what is biasing, and biasing, I mean, is essentially bribing, right? I mean, I know that this guy here acts as an amplifier only if it is in this range. So I cannot just push the papers. Along with the papers, I should push some extra money. That is essentially DC source. So that is happily in this region.
So can you repeat again about the DC operating point?
Okay, you understood that we need to have a DC source,
Yes.
so that it is operating somewhere in this region, correct? So what I'm saying is, if let us say I don't have any signal at all, this is, let us say, operating at this operating point. I mean, let us say it is operating at this point of voltage and current. That current and voltage, we call it as operating point. That is the IV point, voltage and current point at which the device is there operating. That is called operating point. I mean, the lame analogy I usually give is this. I mean, let's say you want to ask pocket money or ask your parents to buy you something. You don't ask them when they are in a bad mood, right? What you do, you make sure you do all the household work, make sure that they are in all nice and happy mood, and then you go and ask. Same thing. You want to ask a favor from this guy, so you don't directly ask it. You basically make it happy and then ask. Great. So now, if I show you an IV characteristics that looks like this, would you call this to be a linear characteristic or a non-linear characteristic? Non-linear. So, which means if I want to amplify power, seems like I need to have some kind of a non-linear device, right? Also remember that only this non-linear device alone is not sufficient, because I could not directly connect this source to the circuit like this. So what is the additional thing I needed to have? I mean, I cannot directly connect the signal and give it to this, right? What was the additional thing we added? The DC bias source or the battery. So non-linearity alone is not sufficient. Along with that, you add some kind of a DC battery or something. I'll say DC source. At this point, if you are true physics, fan, you should ask me a question. But since no one is asking the question, I'll ask it myself and answer. See, what does thermodynamics say? Second law of thermodynamics or first law of thermodynamics? I forgot.
Second law.
First law, yeah. What is the first law of thermodynamics? Energy you cannot create energy, you cannot destroy, you can only convert from one form to other. So here it looks like I had an input power and power is getting amplified. So which means energy is getting amplified. So what kind of black magic is this? We are generating new energy. What's happening? Yeah, it's got to do something with the DC source. And it turns out, as we will see later, what exactly happens is this nonlinear device alone, it is not generating any energy. It is essentially borrowing some power from the DC source, converting that power to your signal frequency. That's all it is doing. We are basically converting energy from one place to another place. That's all. Right? We are no way violating any laws of thermodynamics. Is it okay? This will become slightly more clear when we look at more examples, but that's what happens. So that's how an amplifier amplifies power. It borrows power from a DC source, converts that DC power to a signal power, and that's how you get more signal power. So, overall energy is still conserved. Okay. So which means if I just had a truly linear and time invariant network, remember if I have an LTI system, if the input is at a sinusoidal frequency of f0, the output will also be at the same frequency. In other words, you cannot have any kind of frequency translations with truly linear and time invariant systems. But what we want here is a different thing. We want to convert energy from DC to a different signal frequency. Right? So which means if I want to get power amplification, I can never get it only using LTI systems. Yeah. Okay. If you have an LTI system, it turns out if you apply an input at some frequency, let's say some 1 kilohertz, at the output also will get only 1 kilohertz. You cannot get a different frequency, right? Whereas here what we want, we are drawing power at DC, but we want to convert that DC power to a different frequency, because your signal of amplification, signal of interest might be, let's say 1 kilohertz sinusoid. So here we want some kind of frequency conversion that is not possible with LTI systems, right? So that is something to have. You cannot have power amplification with truly LTI systems. And that's where we kind of use nonlinearity to do the job.
So,
Yes?
can you repeat that exact sentence? Then you said that analog signal source is borrowing power from the DC source?
No, okay. What's happening? We have both of these. What I'm saying is, this nonlinear device, it is not generating any energy of its own. It is simply borrowing some power from the DC source, converting some portion of the DC power to your signal power. You borrow 100 rupees from your parents, saying that you want to buy books, spend 10 rupees on the books, 90 rupees for movies. Same thing. So that's something you should always remember. So the takeaway I wanted to have is this. No, we make op-amps because we want to use a negative feedback, and amplification means power amplification. And with truly LTI systems, we cannot have power amplification. We need to have some kind of nonlinearity and a DC source needed to power it. Is that okay? Cool. So now this is done. So now the question is, how do I basically go and design this, right? For example, let us say I know that I want to bias this nonlinear device so that it is operating at 0.75 volt. I should find out what should be the value of this so that the DC voltage here is so and so. So that means we need to understand how to analyze the circuit. So that's what we'll quickly do. So let me just copy paste this. This can be there. And remember, now this is a nonlinear network. So we'll see what to do. So let's say our first goal is to find out what is this operating point, or in other words, what should be this DC source so that I get the required operating point, or vice versa. I give a DC source, you find the operating point. Right? That's the analysis problem. And for that, we'll assume that there is no change in my Vin. Okay. So we'll assume that Vin is 0. So which means voltage source is shorted. Right? Now let's say this voltage is some Vn and the current In is some nonlinear function of the voltage. Okay. Some nonlinear function we do not know. Now how do you solve for this circuit? I want to find the node voltage and branch current. What would you do to solve? Use KCL, KVL. KCL, KVL are fundamental. You can use for any circuit, linear, non-linear, time invariant, anything. So let us say I apply KCL at this node. Sum of the currents leaving the node is 0. What is the current flowing from right side to left side? Vn minus Vb by Rs. So that is this current. So this current plus the current flowing down, sum of the two is 0, and the current flowing down is f of Vn, some nonlinear function of Vn. Okay. So now, I mean, this is a nonlinear function. Just have to solve for it. No shortcuts. You might have learned some things probably in your undergrad time or something. Use some techniques to solve for it. There is no escape, right? So let us say you solve for it and find out what is Vn if I give some value of Vb. This is essentially a DC operating point calculation. Right? Okay. Now that is not the entire story, because on top of the DC operating point, I also have the signal that I want to amplify. So let us say so you find this and then you add the signal source. Now my goal is to find what is the total voltage here. Right? So let us say because of this Vn you have some additional terms, I'll call it delta Vn. Okay. So which means the current flowing down here is not f of Vn, it is f of the total voltage Vn plus delta Vn. So oh, it's not coming. Oh, yeah, so what I'm saying is now we already, let's say this is the DC operating point. You solve this nonlinear equation, you get the solution, done. But that's not the final thing, because you want to find, in addition of both Vb and Vn, what is the total voltage, right? So which means I'm saying you have Vn plus an additional term delta Vn due to, let us say, Vn. So I'm just marking the voltages. I have not done anything new.
Yes, because initially we should assume it short circuit.
Correct. Initially we wanted to see what is the contribution only due to Vb. That gave us the operating point, right? So the idea to find operating point is we assume that the Vn here is so small that the operating point is roughly the same. So you ignore it to be 0. So you short it and then find the voltages. Okay. So now this is the total circuit. Now I actually have to solve. Now I have two voltage sources. If this was a linear circuit, what would you do? It's a linear circuit. I have two inputs. What do? Do superposition. But unfortunately, life is not that easy, because this is what kind of circuit? Nonlinear circuit. So technically speaking, we have to write KCL for this again and solve it, right? So if I write the KCL, what do I get here? So let me write it down. I now have Vn plus delta Vn. Fine. Now what is this voltage now? This node voltage is Vb plus Vn, right? So let me mark it, maybe this is minus and plus. Minus Vb, so I'll have minus Vn by Rs, plus I have f of Vn plus delta Vn summed up to 0. I've just written KCL, just change the voltages, that's it. So technically speaking, we have to solve this nonlinear equation once again. Right? Now as engineers, one thing everyone unanimously hates is solving equations, and it is nonlinear equation. We already had to solve one nonlinear equation, there was no shortcut. Now if you ask me to solve one more nonlinear equation, that's too much. So that's where as engineers we are smart. We try to get around the problem with some kind of smart approximations, and the approximation is the following, right? See, here the nonlinearity comes only from this function. This part is fully linear. Agreed? Now time travel to your 11th standard or 12th standard time. Let us say I have a function like this. Let us say I already know what is f of Vn. I want to find what is f of Vn plus a small change. How do you find it? Use Taylor series. Taylor series, you guys remember? Not Taylor Swift, Taylor series, okay? So how do you expand this now? F of, not 0, around Vn. F of Vn plus f dash of Vn times delta Vn plus f double dash of Vn delta Vn square by 2 plus all the higher order polynomial terms. Now is where we make the following assumption. We'll assume that the delta Vn we are looking at is really small. By small, what do I mean is this? Let me assume that the delta Vn is so small that the second term here is much smaller than the first term. Right? So which would naturally mean the third term is even smaller, fourth term is even more smaller. So let me assume that I have second term which is f double dash of Vn times delta Vn square by 2 is much smaller than f dash of Vn times delta Vn. So okay, this is my net. If I have 0.1, if I square it, it's 0.01, it is even smaller. Right, that's all. So which means if I what is the inequality? I get delta Vn to be much smaller than 2 times f dash of Vn by f double dash of Vn. As long as my delta Vn is satisfying this condition, I know that the first term will be much greater than all the other terms. So which means this term can be equated as only sum of the first two terms. Is it clear? So let's do that. I am just replacing it with the first two terms, f of Vn plus f dash of Vn times delta Vn, sum of it is 0. This is under the assumption that my delta Vn is so small, and how small it is, it should be smaller than this quantity. The first derivative of the nonlinear function at the operating point divided by the second derivative of the nonlinear function at the same operating point times 2. Right? As long as we are dealing with signals which are smaller than this, we can do this. So now let's see how to solve for this now. So if I look at it here, I have Vn, Vb, Rs, f of En. I already know that sum of all this is 0. Here I see Vn minus Vb by Rs plus f of En, that is 0. So which means I can knock off those terms. I'll end up with delta Vn minus Vn by Rs plus, I'll write it like this, f dash of Vn times delta Vn equal to 0. Does it make sense? So now I just have to solve this equation. And do you think this equation is linear or non-linear? Why non-linear? Huh? I mean f dash of Vn, but what is the variable you are trying to solve for? Delta Vn. So f dash of Vn is a variable or a constant? It's a constant. What is f dash of N? It is the derivative of your nonlinear operating point, I mean nonlinear characteristic at that operating point. That is a number. Correct? So this is now a linear or non-linear equation? Linear equation. Now everyone is happy, we can solve it. So let me just erase some things. So I'll erase this intermediate step. So this is what we'll have, and this is what we have to solve. Okay. So now this is the equation. Let's try to see how the circuit will look like for this, right? So the first term is essentially delta Vn minus Vn by Rs, right? So which means now I don't need to worry about Vb, because in this equation Vb is not there at all. In other words, value of Vb is how much? I mean, if Vb is not there, what is the value of Vb? 0. So I zero it, so it goes off. Correct? So which means I'll have only delta Vn here. Correct? So now you see delta Vn minus Vn by Rs. That is the current flowing in this direction. Right? So this current is what is written here. Maybe I'll use a different color. So let us say this current is what is written here. Now I look at the second term. Second term just says that delta Vn times a constant. So if I were to redraw the circuit, I mean, okay, if it's confusing, think of it this way. You're okay that we have to solve this equation. I'm trying to make a circuit representing this equation, right? So then I see the first term I have is delta Vn minus Vin by Rs. That is essentially this delta Vn minus Vin by Rs. The second current I have is delta Vn times a constant. So I see that the current flowing here is that voltage times a constant. So how do I model this now? Use a resistor, right? I mean, I see that the current leaving this node is the same node voltage times a constant, which you would have learnt in your physics that it's basically a resistor's property. I'll replace it with the resistor Rn. And what is the value of the resistor? 1 by? Yeah. 1 by f dash of V. Is this clear? So now basically this is a simple linear circuit. We can solve for it. In fact, we started from there. We know that it's a voltage division between Rn and Rs. Now it's easy to solve. So if you look at the top level picture, what we have done is the following. I had a nonlinear device, but as long as my input signal of interest is smaller than this quantity, I can convert that nonlinear device into a linear device, and in this case the linear device is a resistor. Right? So this is what we say, we are linearizing a nonlinear circuit. And that works only if my delta Vn, the signal we are interested in, is smaller than this particular quantity. And this circuit, of course, you know this is what we call as small signal or incremental equivalent circuit. This is the effective circuit that we have to solve for finding how much will be the change in the voltages, that is this delta Vn and so on. And remember, this small signal approximation we can do only if delta Vn satisfies this. I am highlighting this again and again. Okay. So which means, remember that this delta Vn, the limit on delta Vn depends on the nonlinear properties of the device and the operating point also. Correct? It is dependent on the nonlinear property and the operating point. So which means tomorrow if I give you a nonlinear device and I don't give you any other information and I ask you if 1 millivolt is a small signal or not, what should be your response? Huh? Huh? You need to give me more information on the device, because for some devices 1 millivolt might not be a small signal, whereas for some other devices even 100 millivolt might be a small signal. It all depends on the particular characteristic and the operating point at which the device is operating. Is that clear? Great. So, yeah, to cut the story short, if you are given a circuit like this, a nonlinear circuit, which is powered by a DC source, and then on top of it you have small voltages added. To solve for the circuit, you do the following. First, you assume that you are finding the contribution only due to Vb. So you assume that Vn is very small, so you short it. And then you solve for this nonlinear equation. There is no escape from that. You solve for the nonlinear equation and find the operating point. So that is the first equation. So this is the first equation. You find the operating point. And then for small changes in Vn, you assume that the DC sources are not there. That is, they are made zero. So which means in my original circuit, I am shorting this. I'll only find the contribution due to the small signals, and as long as my signals are smaller than whatever limit we have for the device, then the nonlinear device can be replaced by a linear device, and for this case is essentially a resistor. So you solve for this small signal circuit, you get what is the value of delta Vn. So this gives me small signal. So the total voltage you will observe at that node will be sum of the two voltages. So total is operating point plus small signal. Is that okay? I'm guessing you might have seen this earlier. So again, repeating, you have to solve first for the operating point. There is no shortcut. You solve the nonlinear equation, and for finding the operating point, you assume that the signals are not changing. That is, the small signal voltages are 0. Once you find the operating point, then to find the effect of the small signal, you check if the signals you are looking at are smaller than the limit you have. If so, then the nonlinear device can be replaced as a linear device. That gives you the small signal equivalent circuit, wherein you de-energize all the DC sources, and then now you have a linear circuit. You solve for the linear circuit. Total voltage will be the operating point you get plus the small signal quantity you compute. Okay. Now, of course, I mean, if you see this graphically, it's even more intuitive. Right? See, let me erase all this. Yeah. See, what we are saying is the device is operating at this operating point, and my range of delta Vn is small. So which means maybe it is operating in this small range of voltages. So which means if I zoom in the characteristic of the device in this range, even though the actual characteristic is nonlinear, around a small range, how will it look like? Linear. That's all. I basically go and zoom this like this to look linear. So that's essentially what we are doing. Oops. So if I draw the characteristic and zoom in, it will look like this. Nicely. So which means now I can say that my small signals are going to be swinging in this range, in that small range, or here in this magnified range. And remember, this is the operating point. So I can say that my small signal IV characteristics, I call it delta V and delta I. This is how it will be. Because now we are only interested in the small signals, and they are going to be changing in and around this operating point. Essentially, I am shifting the origin. You might have seen in your math courses. It's essentially shifting the origin and axis, calling this to be the origin. Because origin is essentially a point which is not moving. For small signals, the DC operating point is not moving. So I'll say that this is the case. Now look at this small signal IV characteristic. It is lying in which quadrants? Second and fourth. So for small signals, what kind of a device this is? Active device. Okay. So that's the other thing. So I will say this is small signal. So that is why people say that some devices are active, some devices are passive. But strictly speaking, in real world, you cannot generate any energy on your own. All devices are passive. Just that some nonlinear devices, when operated at a particular operating point, for small signals, they are active devices. So amplifiers are essentially nonlinear devices which in some particular range of voltages for small signals are active. Okay. Is that clear? Because see, in circuits, what is the one element that can generate any energy? Voltage source and a current source, right? So if I look at the IV characteristics of a voltage source, how will the IV characteristic of a voltage source look like? Voltage is constant irrespective of the current. So this is the only active element within quotes we can have. But again, thermodynamics says you cannot generate any energy. So even a voltage source, this is a battery, it is not generating energy, right? What is it doing? It is converting chemical energy into electrical energy, and that's all. But as far as electrical engineering is concerned, we will be oblivious to all other forms of energy and say that, hey, I know only electrical energy, and here is one device that is generating energy on its own, that is an ideal voltage source. I'll call this active. But remember, in practice, nothing is active. Everything is passive. Yeah.
So can you explain this?
Yeah. So what I'm saying is, voltage source is an active device, ideal voltage source, because it can provide energy. But what I'm saying is, even an ideal voltage source, it's a battery. It is not generating any energy. It is converting maybe chemical energy to electrical energy or something. So there also it is not active. Is what I'm trying to say. Strictly speaking, at top level physics, this is passive. But when we come to electrical engineering, we will assume that this is coming from thin air and it is getting generated. Is okay? So that is with how to deal with one port, or I will maybe make the jargon here. Battery, everything is passive, right? Because see, strict definition of passivity, if you want to follow, is that if any element can, or activity, right? If any device is active, it should be able to generate power on its own. But thermodynamics says you cannot do it. Strictly speaking, you are doing basically conversion from one form to other. But that said, if you are dealing with electrical systems, you know only electrical energy. So any energy coming from different sources, they are all kind of black magic tools. So that's why we say voltage source is active.
So if someone asks me, tell me some active sources.
The question should be, what do you mean by active? Are you talking about free energy, or you are asking about some device that can generate a particular energy from different energy?
So if someone says sun is active source or passive source, because it has some nuclear reaction also.
Okay, maybe the talk is going somewhere. If you want, we can take it offline. See, sun is also not generating. It is because of nuclear fusion, right? It is dying. Sun is essentially dying, right? Maybe after a few billion years, it will die off because everything kind of fuses out. So nothing in the world is active on a philosophical domain. Okay, so let's not go too much. But hopefully this. Okay, if you want, we can discuss later because it's digressing somewhere else. Okay. So yeah, one jargon to say, this is what we call as a one port device. By port, we say that any pair of terminals we call as a port. Here I have two terminals, so we call this one port device. And so we saw how to make an amplifier with a one port device. And if the one port device has to act like an amplifier, it should have some kind of a negative slope in its nonlinear characteristic. Is that okay? And for small signals, this nonlinear characteristics can be approximated as a linear characteristic, and that's essentially a resistor, right? Or in other words, a small signal model for a one port nonlinear element is, what is it? It's a resistor. I mean, it's a nonlinear one port device. For small signals, it's a resistor. So now, and it also turns out that there is a real device that has characteristic like this called as tunnel diodes. If you want, you can check it out. But we don't use such one port devices for amplification for simple reason.